Okay, welcome to an introductory lecture on modeling of ground heat exchangers. And, well, let's get started. So, why do we want to do this? Well, we need numerical models of ground heat exchangers for several purposes. So, the first one is design. When we're using simulation-based design tools like GLHE-Pro and EED. All right, in that case, what we're doing is we're using the simulation and adjusting, for example, the depth or possibly the number of boreholes, the configuration and the depth automatically to meet a user-specified minimum and maximum entering fluid temperatures. All right, so in that case, the engine is the simulation. We need this if we're doing energy analysis and whole building energy simulation programs like Energy Plus or eQuest or other programs. We need some sort of model to predict, if nothing else, what's the fluid temperature coming back to the heat pump or heat pumps. And then furthermore, if we'd like to optimize the thermal design or the hydraulic design, the system configuration, the controls, the economics, generally our best tool, or maybe most powerful tool, is simulation. It gets pretty hard to build and test a ground heat exchanger for 30 years to see what happens. So that's why we typically rely on simulations. Main goals of this lecture are to introduce, first of all, what's the problem? Secondly, what concepts are used for modeling ground heat exchangers? And we're going to look at a very simple approach. It's not a state-of-the-art approach, right? But this is intended to give the student a better understanding of ground heat exchanger modeling. And there'll be further lectures on improvements, significant improvements to this model, right? In this lecture, it's not intended to give a detailed survey of the entire field. It's not intended to introduce the latest methods being applied. They're far too complicated and require more attention than what we can afford in a single lecture. Okay, so a ground heat exchanger is presents us with a fairly complex three-dimensional conduction heat transfer problem. It's got what I would consider to be very complex geometry, and that's because we have a U-tube, which is, even if you just take it in the, say, cut a slice at a uniform depth, you see you've got two circular tubes. They're inside of another circle, the borehole itself, and then you've got a large domain outside that. So it doesn't really fit very well into, say, a Cartesian coordinate system type geometry. We've got a wide range of length scales, so when we're modeling the heat transfer inside the borehole, we might be interested in heat transfer over millimeters. Right? The pipe wall thickness is usually a few millimeters. But in larger ground heat exchangers, or even in single ground heat exchangers, which may be, say, 100 meters deep or deeper, but in large ones, we might have a field that's several hundred meters in each direction. And so we've got a wide range of length scales to resolve. We've also got a very wide range of time scales. So if we're looking at the response to, say, a change inside the building, a heat pump turns off or on, the response from the ground will happen in a few minutes. But at the same time, the ground has such a large thermal capacity that the heat buildup, say, over time, or cold buildup, could take decades. So we have this very wide range of length scales and very wide range of time scales. It means it's generally impractical to solve it numerically, and by numerically I mean finite element method, finite difference method, or finite volume method. All right, and yes, it's possible to do a simulation of one borehole or a few boreholes, given enough computer time, particularly if you're a researcher, and if you're not interested in solving for 20 or 40 years. right? But in general, it's not even practical for a researcher to simulate, for example, a 150 borehole system by while modeling every borehole um, and resolving the length scales. So because of that reason, that's why I say it's generally impractical to solve. Maybe not. It may be impossible to solve the 100 borehole case um, if you resolve every borehole independently and you account for all the length scales and time scales. There just may not be enough computer power anywhere, period. Um, but even if it can be done for a few boreholes, it's generally not practical for design purposes or energy analysis purposes. So there have been a wide range of simplified methods. Some are better than others, of course. And one sense, all the methods, or I think all the methods, most of them work until they don't. It's kind of a funny way of putting it, but it means that it works for some problems and until you run into something that wasn't envisioned in the model development, then you no longer get such a good answer. So it helps to be aware of that from a design engineer standpoint. So in fact, I've already mentioned, that it's a three-dimensional conduction heat transfer problem. Well, for some problems, it's not just conduction. We also have groundwater flow to worry about. So, but there's many cases for which groundwater flow, the effects are negligible. And so that's where we're going to start. Okay, so in terms of methods, there are analytical methods, generally what's known as a line source. We'll be talking about the infinite line source in some detail today. There's also a finite line source. There are cylinder source approximations. There are numerical models, as we're just discussing how they're not generally practical for real-world problems that go beyond a few boreholes. There are custom thermal networks, sometimes called TRCM, thermal resistance capacitance network is method. Or, well, there may be different acronyms, but they're, say, customized networks of resistances and capacitances that, say, match a single borehole. There are response factor methods, so a number of these were originated by Professor Johan Claesson of the University of Lund, Sweden, and two of his PhD students, Per Eskilsson and Göran Hellström. They developed what I call long time step G functions. They're not really intended to go down to minutes or even a few hours, but more, let's just say 12 hours and up or something like that. So in the 1990s, my PhD student, Cenk Vusterk, and I developed or extended these response factors to go down to short time steps. And then later, another one of my PhD students, Xiaowei Xu, and I developed short time step response factors that are a sort of simpler approach to what Cenk Vusterk had done, and also pretty accurate. So that's, I guess, we more commonly use that. Xiaowei also developed a hybrid response factor and numerical model so that we could have, for example, variable convection heat transfer or variable convection coefficients inside the borehole. Okay, so in a little bit more detail, there's an infinite line source. It represents the entire heat rejection or heat extraction as a line source in infinite media. In other words, it's really a one-dimensional radial only problem. And the way it's used, and I'll show you this in a little more detail in a minute, it's used to compute the temperature of the ground at the borehole wall. And then there's a separate model of the borehole that involves a borehole resistance and possibly also the fluid flow and the temperature difference across the fluid to predict the fluid temperature, say, exiting the borehole. There's infinite cylinder source, and there's several variations that differ based on what's inside the cylinder. So you can have an empty cylinder or a cylinder that's filled with the same material as the ground. There are another variation that includes let's see, one or two resistances. That's if you look at this; these are covered by Carslaw and Jaeger, or if you look at Thomas Ray Young's master's thesis. Ray Young was one of my master's students. He developed something called the buried electrical cable model, which is how Carslaw and Jaeger originally envisioned it. So the material inside the borehole was different, and there was also a resistance, one or two resistances, now I've forgotten. And we actually looked at using it, but it tended to have a bit low accuracy, under 6 hours in time. So that's when we came up with this GSHP-U and Spitler, which has a 1D numerical model inside the borehole used to generate the short time portion of the G function. The G function is a response factor that we'll talk about later. Okay, more recently there have been a number of finite line source models. These represent the heat rejection or extraction as a finite line source in infinite media, so you can have end effects. And with this, you could represent an entire borehole as one finite line source. But if you wanted to get better accuracy, you can actually divide the borehole up into, say, 10 or 15 or so individual segments, each of which has its own heat input. And the trick to that, which we'll discuss in the future, not even in this lecture, is how to determine the heat input into each of the segments. Okay, so we're mostly going to look at line source in this lecture. We're going to develop an example where we actually do some calculations. The line source can be thought of as a point source in a planar sheet, right? There's no analysis in the z direction, the height direction. It's often said to be developed by Lord Kelvin. In fact, sometimes people even cite a paper. Well, we'll call it a paper. If you look at William Thomson, Lord Kelvin's, his collected works in 1884, he has a chapter which mostly comes from, I'll say an 1880 paper, but actually it's an 1880 article for the Encyclopedia Britannica. Right, and there he treats the Fourier solutions for conduction heat transfer. And this is based on a point source in a three-dimensional space. That point source solution comes from Fourier. What Kelvin did was to apply it to a number of situations. But interestingly enough, line source is not one of them. So, in a sense, I'm not really sure the reason why it got this, or people call it the Kelvin line source. It's, I may give a separate short lecture on the history of this. But in any case, it's a fairly simple model. It was first popularized for ground heat exchangers by Ingersoll and Plass, and we will look at that. Okay, so when we talk about boreholes, here's a couple borehole designs. On the left is what we might imagine as being a typical North American design. And what you see here is you see the borehole, this sort of dark brown, has been drilled in. You see it's covered over a soil. That's correct. So typically it's drilled. The tubes are left sticking out of the ground. Someone comes in and does some trenching and connects the tubes below ground. That's why I've got it shown like this. There's a U-tube in there, and typically it should be grouted. In other words, should be backfilled with a material like bentonite clay designed to keep water, groundwater from infiltrating down the borehole. So you can imagine if you spray pesticides or herbicides at the top, right, you don't want them leaking in and running down here. So typically that's why people grout the borehole here. The European solution, or not, I shouldn't say European, Scandinavian, mainly Sweden, Finland, Norway primarily, where they have a lot more hard rock. They actually have a typical solution involves it's much more like a water well. So what they'll do is they'll case down from the top of the well down into the bedrock, right? And then below that, it's open to the bedrock, and it's just filled with groundwater. And of course, the groundwater in that case will come up to the level of the whatever it is on the outside of the borehole, where it'll come to equilibrium. And oftentimes they just put a weight on this. We often need a weight to get ours down, but they typically need a weight. So in that case, the U-tube just sits in the hole. And then this is all sealed, so the steel casing and the well top keep you from getting groundwater inside. And we're mostly going to be talking, we'll be talking actually mainly about the grouted boreholes. Okay, so if you can imagine the analysis for a line source where we're really not looking at the end effects, then what we have in a plane is this. We have a U-tube, right? And here's the tube with water or water antifreeze mixture inside. It's backfilled with some kind of grout, and then there's an outer borehole wall. The way the line source works is we take a heat input at the center. We pretend that this is all filled with ground, not with grout, no tubes, right? We just assume that we're putting the heat into a hole in the center. Then we use the line source to predict the temperature that we would get at this radius of the borehole. So I think maybe the first thing you should be aware of is right off the bat there are some approximations that are made that mean that the accuracy isn't 99.999%. Okay, that's okay. It's still good enough to do a lot of things with, but before we worry too much about getting the solution right to the 10th decimal place, right, you should just be aware that first of all, the line source model has this approximation of what's inside. Secondly, you'll often see drawings like this where the U-tubes, nicely symmetrically placed in the center. And of course, in practice, it's often the case that, first of all, these holes don't go into the ground straight, so they may sort of corkscrew down. Corkscrew is a bit of an exaggeration, but they may twist and turn some. And even if they're perfectly straight, it's unlikely the U-tube's going to sit exactly in the center, so symmetric. But we often think of it as, on average, it has something like this, where the spacing between the two tubes is about equal to the spacing between the tube and the outer wall. Right, and there's some empirical evidence for it, but not a lot of hard proof. Okay, the line source then, as introduced by Ingersoll and Plass, although there had been some earlier authors who had presented something similar, is again, predicts the temperature of the borehole wall. The analytical expression, which you get by integrating Fourier's point source, right, gives a temperature difference at the borehole wall of the heat input divided by 4 pi times the conductivity of the soil, multiplied by this exponential integral, right? And where the lower limit is r squared over 4 times the thermal diffusivity of the soil times the temperature. Times the time, right? And when we solve this integral, then we can find the temperature difference. Okay. Now, the nomenclature. The delta T is the change in ground temperature at a distance r from the line source, and we're going to typically apply this at RB, the borehole radius. Q is the heat transfer rate per length of line source, so watts per meter or BTUs per hour per foot. T would be the time duration. Of course, if you were using American units, then the time duration would be in hours, not in seconds. The radius would be in meters or in feet. The soil thermal diffusivity meters squared per second, or, and I say feet squared per second, but everything, this all has to be consistent here, so you might want to make that feet squared per hour. And the conductivity of soil typically given as watts per meter K or BTUs per hour per foot degree Fahrenheit. Okay, so that's the end of part 1. We'll come back with part 2.